Okay, in few previous chapters, I already introduced how to use point defect to strengthen materials, right? And there are different types of the point defects, such as the vacancies and the interstitial site and substitutional atoms and self-substitutional atoms. Uh, those of this point defect can be regarded as the kind of impurity to strengthen the material's property. Okay, and the issues we have to address is that when we combine two elements, of course, one is the matrix and the other one is the we can say it's a point defect for strengthening the materials. And what is the resulting equilibrium state? Okay, and particularly we specify the composition, like the weight percent of the matrix and the point defect, and also the temperature. Okay, if we specify the composition and temperature, then the things we have to discuss is how many phases form and what the composition of each phases is and what is the amount of the each phase is. Okay, so we can look at the figure here when we combine two elements, okay, copper and nickel. We combine two elements, copper and nickel. Okay, one matrix and the point defect, or no, and we can discover that in this kind of solid solution, there are two phases formed. Okay, we call it solid solution. There are two phases formed. Okay, and one is in the here in this region. It's a homogeneous structure. Okay, homogeneous structure, and the second one is the region outside from this phase B. Okay, okay, so there are two phases, one and two. Okay, one and two. Okay, so let's look at the solubility. Solution can be solid, liquid, or gas. Okay, those are single phase, and mixture is more than one phase. Okay, so how to find out the solubility limit, which is the maximum concentration for which only the single phase solution exists, right? So let's consider a question is that what is the solubility limit for sugar in water at 20 Celsius? So how to plot the figure like this? How to plot the figure or how to plot the phase diagram of sugar and water? So the phase diagram is composed of temperature and the composition of sugar and water. Right? It's kind of a high school chemistry course. Right? So we can adjust the composition of water and sugar, right? And homogenize them in a fixed temperature, right? When the solubility limit reached, you will see a solid precipitate. So we'll see a solid precipitate. That means the two phases coexisting, liquid and solid, right? Liquid and solid. Okay, therefore we can do the experiment to plot the phase diagram of sugar and water. Therefore, we can find out the solubility limit, right? This line, this curve is called the solubility limit. Okay, okay. So the right side of this solubility limit is two phase. It's two phase coexisting, liquid and solid. And the right side of this solubility limited is single phase. Only liquid phase existed. Okay. Therefore, what's the answer of this question? Was the solubility limit for sugar in water at 20 Celsius? Okay, 20 Celsius, right? Therefore, we can find out here, right? Find out here. So it's 25% weight percent for the sugar that can be dissolved in water at 20 Celsius, right? Right. So if we say at 20 Celsius, when the composition is higher than 25 weight percent, that means coexisted. Okay, that means coexisted. Right, two-phase region, they are coexisted, right? And if the composition is smaller than 25%, that's mean only the single phase, liquid phase coexisted. That means the syrup, okay? Okay, so let's look at if the phase diagram of water and solid, right? Sugar, that's a solid and liquid phase diagram. If we look at the metals, two metals, right? Two metals can be, can be plot of the phase diagram, right? So how to plot a phase diagram? For example, for two metals, like for metal A and metal B, how to plot the phase diagram? So we have to do the experiment to melt pure metals and alloys and collecting uh, the uh, the time versus temperature. Okay, so for example, let's look at the figure, the left figure. So for the element A, it's the pure metal. It's pure metal. It's pure element A or pure A metal. Okay, so we melted, right? Melted and cooling down. And cooling down when it reaches specific point temperature, and this temperature will remain for a certain time, for a long time. And when its time reaches a certain point and the temperature began to drop dramatically, okay, till to the ambient temperature or room temperature, okay, and the time between 0.2 and 3, if this time is longer, so what's that mean? What's the meaning of what's the physical meaning of this duration from 0.2 to 0.3, right? If the time is longer, what's that mean? That means this materials or the element A has higher latent heat that can absorb the higher heat, higher energy, okay, higher energy. Okay, so we can mapping the A curve to a phase diagram. So what's the line on the right? I mean the phase diagram. Which line in the phase diagram represents uh, the curve 8? I'm saying this is the phase diagram. Okay. Okay, so in the phase diagram, which line represent the A, the curve A? You know what I'm saying? So we can mapping the curve A to where? To here, right? To the straight line. Okay, and we can mapping the temperature for a phase transformation to this point. Right? Right. So this vertical line means the A. Okay, therefore we can say, oh, the melting temperature of element 8, we can find out here at this point. Okay, and if we adjust the composition between A and B, element A and B, for example, like 75 weight% of A and 25 weight% of B, say it's a B curve, that's a B curve. The same, we just melt this alloy at high temperature and cooling down very slowly, and we'll find the phase start change at the 0.2 to 0.3, right? And then the temperature will drop to the room temperature. Therefore, we can mapping the 0.2 and 3 on the curve B to its phase diagram here and here, right? And then we can keep adjusting the composition of element A and B, say 50-50. It's the curve C. And we just run the same experiment, just melt it at a high temperature and keep cooling down. And you will start to start the phase transformation at 0.2 to 0.3, right? And the temperature just keep drop to room temperature. And we map in the 0.2 and 0.3 to the point here, to the phase diagram here. And the same, we just adjust the composition 25 weight% of A and 75 of element B. We get a D curve, and we mapping the phase transformation point to here, to phase diagram. And for the curve E, that represents the pure metal or pure element B. Okay, therefore we can mapping this phase change temperature, okay, to the phase diagram here. Okay, therefore this line represent what? Represent the behavior of pure element B. Okay, and then we can plot this figure, right? We're going to connect at each point. Okay, this is connected. Okay, we got this phase diagram of element A and B. And for the upper line, is called the liquidus line, and the lower line is called the solidus line. So that's mean the composition and temperature is located above this liquidus line, and the phase is totally liquid. And if the point below the solidus line, that's mean the alloy is totally solid. And if the point, I mean the composition and the temperature is located within this liquidus and solidus line, like here, that's mean the alloy is two phases coexisted. Okay, that's mean the solid and liquid coexisted within this range. Okay, sorry. Okay, within this range. Okay, so we have to do the numerous experiment. Okay, and then this phase diagram can be plotted, right? Okay, so alloys are frequently used in engineering applications. Alloys are either single phase or multiple phase. So we already know what a phase definition is. So a phase is any portion of a system which is physically homogeneous. Okay, it's physically homogeneous. A system which is a physically homogeneous and bounded by surface. Okay, which is separates from other portion. So remember that this figure, we already know it, right? This figure. Okay, phases has the same structure throughout. It has roughly the same composition and properties throughout, and has the different interface between the face and any surrounding faces. Okay. So I will introduce you the a rule called the Gibbs face rule. Okay, that relates the number of possible faces for system with number of species present and the degree of freedom. Okay, so a scientist, the Gibbs, just define the face rule like the 2 plus C equals to F plus V. This 2 means 2 parameters, temperature and pressure. Okay, this 2, temperature and pressure. Okay, and the C is number of components. F is degree of freedom, and the P is number of phase. Okay, it's number of phase. Okay, so let's look at the example here. So for single component phase diagram. Okay, can be also called the PT diagram, pressure temperature diagram. Okay, for example, this figure shows the single component magnesium. Okay, magnesium. Okay, so if the we say the situation is at point B, I mean the situation for the magnesium is at point B. So how many degree of freedom? How many degree of freedom it has? Okay, so let's look at this. Like how many components of this phase diagram has? 1, right? Magnesium. Magnesium. And how many phases at point B? It's an interface between solid and liquid. It's not an area, it's just a line. Therefore, any phase on this line is on this line. Point on this line. Any phase located on this line is 2 phases coexisting. Okay, 2 phases coexisting. Therefore, there are 2 phases. So how many degree of freedom it has? 1, right? Therefore, if we say the magnesium, the phase diagram of the magnesium, or we say the point B of the magnesium has what? Has 1 degree of freedom and 1 degree of freedom. Okay, so what's that mean? That means we can only modify 1 parameter, pressure or temperature. Okay, if we want the 2 phase coexisting. Okay, that's if we want a solid and liquid phase of magnesium coexisting, we can only control pressure or temperature. Okay, 1 degree of freedom. And we say, how about the point A? Point A, this is the point B, right? This is the point B. How about point A? So how many components? Of course, 1, right? Magnesium. How many phases? 1 phases, right? Only liquid magnesium, right? So in this region, okay, any conditions in these regions are liquefies. Okay, therefore the point 8, how many degree of freedom it has? 2, right? Is that clear? 2 degree of freedom. What's that mean? That means we can just modify or control its pressure and temperature. At least this point is within the range in the 2 phase in the liquid phase range. Okay, so how about the point X? How many degree of freedom it has? The point X. 0, right? So we have to find a three-phase point, three-phase coexisting point. Its degree of freedom is 0. Therefore, we can only control the pressure and temperature at the specific points that the three-phase point can reach. Okay, therefore we say, okay, still the component is 1 and the phases is what? 3, right? So degree of freedom is 0. 0. Okay. Let's look at the solubility and the solid solution. So unlimited solubility. So some combinations of materials only form one phase when mixed in, no matter the ratios of each species. For example, like water and alcohol, copper and nickel. And this system have unlimited solubility. Okay, and such systems can also form solid solution, which are different from mixtures. Okay, therefore, just know the nickel and the copper, the solubility of the solid solution, nickel and copper, is unlimited. It's unlimited. Okay, it's unlimited. So we have to consider why the solubility is unlimited. Solubility, I mean, that's the one homogeneous phase. Okay, homogeneous phase, which is different from mixture. Okay, different from mixture. Okay, so we'll discuss this later. So what's the mechanism, or what's the factors to causes this unsolubility, unlimited solubility? Okay. Hey, in limited solubility systems, one species can form a single phase solution with another below a certain composition. Okay, any excess added afterwards precipitates out as a second phase. Okay, such as the salt in water or sugar in water. Okay, so if we just has the solubility, has a solid solution of copper and zinc, when the amount of zinc is beyond a certain composition, the second phase will precipitate. Okay, will precipitate. Therefore, we can find out two phases coexisting. So one phase, one homogeneous, physically homogeneous phase, one phase, and two phases. Right, one phases and two phases. Okay. If the second phase precipitates, so we know this solid solution has the limited solubility. Okay, has limited solubility. Okay. And in metallic materials, forming a solid solution often results in solid solution strengthening. Okay, so what's the mechanism of solid solution strengthening? What's the mechanism? Can you explain the reason why, or can you explain the mechanism of solid solution strengthening? Okay, here already mentioned that the solid solution strengthening increases the resistance to dislocation movement. Okay, so the point defect in the previous chapters, we already discussed about this. The point defect is like a barrier. It's like a barrier to stop or to retard the movement of dislocation, right? So this dislocation move will stop, right, by a barrier. Okay, it cannot keep moving. Cannot keep moving. Okay, it's it's called the solid solution strengthening. And what's the degree of solid solution strengthening? I mean, how to define, how to add the point defect, or we just randomly choose, we just randomly pick up one element from the periodic table, or we have any rule, or we have any criteria to pick up the point defect for the solid solution strengthening. Well, basically you can consider two vectors. One is the size differences, I mean the atomic radius, the differences in atomic radius. And the second is the number, the amount of alloy element added. Okay, and the large differences in atomic radius of the alloy results in increasing the strength, increase a lot the its mechanical strength or materials property for this alloy. Okay, and the greater the amount of the alloy element added, the greater the strengthening. So you can think of why the differences in atomic radius is able to increase the material strengthening. Why? You have to explain this reason. I mean, explain the mechanism. Okay, and you also need to explain why the greater amount of the alloy element added a greater strengthening. Okay, we cannot just read this text. We have to think about it in your deep mind and try to explain this, or try to plot an image, and that image represents this mechanism of solid solution strengthening. Well, material science sometimes is quite abstract. It's hard to write it down in text. However, you can try to image, you can try to think, or imagination should exist in your mind. Okay, so look at this. This for the differences in atomic radius of different point defect. Okay, and the matrix atom or the lattice atom is copper, and the alloy element, or say the point defect element, is with different atomic radius. Here, the first one is beryllium, and silicon, and tin, aluminum, nickel, and zinc. Okay, so why? So when you look at this figure, you can realize the reason why the large differences in atomic radius can improve the material strength. You can see the lattice distortion, right? The lattice distortion here in this region, right? The lattice distortion here. There's a substitution atom, which is a smaller, whose atomic radius is smaller than copper, and the lattice distortion around it, right? So you can think of, if there's a dislocation, edge dislocation, when you move, you will hit it, right? You will hit this lattice distortion. You can think of that. Okay, there's a straight wall. There's a straight. Just keep walking straight, right? And when the rule is kind of change its direction, therefore you have to spend higher energy to turn right or turn left. Is that right? Can you understand this kind of yeah. So the same situation of this tin alloy element, okay, Okay, this atom whose atomic radius is larger, much larger than the copper, than that of the copper, right? And what? And this lattice will be distorted, right, in this region. The same if this location move, it will feel, oh, it's hard to keep moving because this the road is, you know, the directions change. Can you imagine that, right? When this dislocation hit, when this dislocation hit this lattice distortion, it has the higher energy to keep moving forward. Okay, and let's see if the point defect or the substitution atom whose atomic radius is similar to the lattice atom, and this dislocation will feel, well, this row change a little bit, direction change a little bit, but it's still I can still, you know, keep moving forward. There's no much barrier in front of me, in front of this location. Okay, so if we do the tensile test of different alloy, if the atomic radius has huge differences, we can find out what? We can find out the Young's modulus has huge difference, right? Right, you can see this, the Young's modulus slope. The Young's modulus is the Young's slope, right? The slope. Oh, sorry, I'm wrong. Oh, it's not stress. Sorry, it's wrong. It's not Young's modulus. It's just the unit stress. Sorry, it's the unit stress. So we can see this figure plot the composition of the alloy elements corresponding to the unit stress. Right, so the higher the huge differences of atomic radius provide the higher Young's higher yielding stress, right? Higher yielding stress. Okay, also this strength yielding stress is linearly related to the amount of alloy elements. Okay. So the criteria for a solid solubility. The first one is a crystal structure. Second one is electronegatividity, and the third one is atomic radius, atomic size. If these three vectors are similar, that mean what? That means its solubility is higher, or you can say you will reach the unlimited solubility, right? As we already mentioned, the nickel and copper, yes, the unlimited solubility. You can see you have the same structure, FCC, and electronegatividity, and almost the same atomic radius, right? Therefore, nickel and copper are totally soluble in one another for any proportions. Okay, therefore this alloy, nickel copper alloy, has the unlimited solubility because we just have the same size, same structure. You know, I can replace you, you can replace me, whatever, right? So we have the unlimited solubility. Okay. So the effect of the solid solution strengthening on properties are the unit stress, tensile stress, hardness, okay, of the alloy are better than those of pure metals. So the solid solution strength is always higher than those of the pure metals. Okay, yeah, because what? Because the dislocation movement is stopped, right? It's retarded or silent. Those solid solution has the higher resistance to dislocations movement. Okay. Okay. However, those alloys ductility is lower than that of the pure metal. That's for sure. You have the higher strengths. You have the higher strengths. Of course, your ductility will become lower. That's for sure. That's for sure. And the electroconductivity in alloy is lower than that in pure metal. That's for sure. So we say the solid solution, what's the application of the solid solution? It totally depends on your application. Okay, for some like electrical industry, we always need a very pure metal for electron transformation or for electron or electron movement. Okay. Of course, the alloy has the higher resistance to the creep. Okay, so you have to consider the application. For example, if this parts or this component is using the like the turbine blade, while the turbine blade is always operating at elevated temperature, right? Therefore, we have to consider its creep. Okay, therefore the resistance to creep can be strengthened by the solid solution. Okay, and let's think of the other question is that how about the thermal conductivity? Right, we have to think of the thermal conductivity. Well, we already discussed the mechanical properties like yield stress, tensile stress, hardness, and ductility, and the electrical property like electroconductivity, right? So how about the thermal property? So which one should have the higher thermal conductivity, alloy or pure metal? Alloy or pure metal? Okay, let's think of these questions. The engine block in your motorcycle, scooter, or car. Its materials is always aluminum alloy. For casting alloy, aluminum casting alloy. Okay, because the aluminum has the relatively high thermal coefficient of thermal conductivity. Oh, sorry, a relatively high thermal conductivity. Right, that's mean you can transfer heat very quickly. However, we cannot use the pure aluminum, right? Because it's soft. Its mechanical strength or property is not strong enough. Okay, therefore we have to use the aluminum alloy. So in the casting aluminum alloy, the aluminum content is about 60 or 70%. Okay, therefore this alloy's thermal conductivity is much lower than the pure aluminum. Right? However, we cannot use the pure aluminum, right? Or I already mentioned that because the mechanical strength is not stronger. So it's kind of a trivial things we have to find a balance. We need the stronger strength, right? And we also need high thermal conductivity. Okay, so we have to find the balance between the strength and the thermal conductivity for the engine block. Okay, so I'm not meaning that okay, which one is better, but I just want to emphasize on we need to find out the balance the optimum balance for your application. Okay, and this kind of alloy, well, whether this kind of alloy can be used in the turbine blade or this alloy can be used in the engine block. Okay, so for material science engineer, we have to consider lots of issues in the real applications. Okay. Okay, so this figure shows the mechanical property corresponding to the person of the alloy element. Okay, zinc in copper. Okay, zinc in copper, and the atomic radius of zinc is similar to copper. Okay, similar to copper. So we can see the higher content of zinc, its yield stress keep increase, right? And its maximum yield stress is about it's about 130 something here. It's right here. Okay. Of course, the higher content of the zinc elements to cause its electric conductivity decrease dramatically, right? You can see that, right? The yield stress increase and the electric conductivity decrease. Of course, it's tensile stress increase. It's also the mechanical property. Okay. Okay, so today's course, I'm gonna stop here on. I will just have the other videos to describe the phase diagram in more details.